So hello everyone and welcome back to this next lecture in the DC to DC converter series, and this is where we had left off when we were simulating the forward converter. So we had basically replicated the files of the flyback converter. We had made some changes. We had added a third winding and we had added a diode. So to go back here, we had connected a third winding to the DC supply and we had put a diode in series, and this is the transformer. And in this transformer, you can see that there are the usual two windings that we had before, and besides these two windings we have a third winding as well, right? So in this video we are going to edit the parameters of this particular circuit, right? So as always, before I start the video, a bit of brief background that if you're interested in these kind of video lectures but you would something a little more comprehensive, I have an full-length online course on the MOOC website Udemy. So the very first course which I have is simulating power electronic circuits using Python, and in this I talk about the basics of how you can use Python to simulate circuits. So there is a little bit of background on how to install software, Python power electronics, some basic about circuit theory, a little bit about power electronics in general, and finally there is a case study of how to simulate a buck converter. If you are interested more in the signal processing side, I have another course which is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how we can use Python for signal processing purposes. So there is a bit of brief background about signal processing. There is tutorials on how to use Python packages like NumPy, SciPy, and the signal package within SciPy to be able to design, analyze, and implement filters, right? And finally there is a case study of how to design and analyze a low pass filter and a notch filter. The latest course which I have is on the magnetic side. So it's called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how we can simulate magnetic components like inductors, coupled inductors, and transformers using Python power electronics. And finally there is a case study of how to simulate a flyback converter, right? So the links for these courses is provided in the description for this video. If you're interested, please do check it out. So coming back to the lecture, so we had added these circuit files, and this is of course after we had edited the circuit parameters. We had created a new folder for the forward converter. So just in case, let's go and click on the process circuit schematics again. Okay, now that we have this, you see that there are a couple of errors. So let's go and check out what the error is. There is an error in two winding transformer between 10G and 29G. So let's go see what that is. So 10G is this one, that is variable resistor 1, and 29G is this one, right? So surprisingly this didn't change because I think there is a typo. Now I realize there's a typo. This should have been winding 1 transformer 1, and this should have been winding 3. This however is winding WW. So actually I can change this now. Let me change it. So I'll make this 1, and I'll make this 3. That wasn't right. Winding 3, right? So this should fix it. Let me save this and go back to the browser. Now when this error is there, the process circuit schematic button disappears, so you just have to click on add circuit schematic again. It gives you a blank form, but you don't have to add anything. What's important is this button. So let's click on the process circuit schematics button again. And this time there are no errors, so we're good to go. But most importantly, when you process the circuit schematics, it creates dummy parameters for all the variables, right? So for example, now in most of the cases I'm going to import the variables, right? So like for example, if you go to the folder, we already have the parameter files from our previous simulation, which is the flyback converter, so we can use them to begin with. So let's do that. Okay, I am in the buck filter, so let me go and add the buck filter params. we might have to make some changes, but we will very soon. Here there would be a change. Here we have to actually manually make a change because there has been a change in the circuit itself. That is, we have renamed a component. Okay, so ammeter, it should be in the resistance, that is this one. So you see that I'm just looking for that. Yeah, these are the resistances. You see winding 3 resistance and winding 1 resistance. So this is the new one that we've added, which does not show up because it's not in the flyback converter. And this one is the one which has been renamed. And as you can see, this does not have the resistance either, right? So these are things we need to change. So let's go and change them. So let's just start with the very beginning, that is ammeter. So we have winding 1, winding 2, winding 3. There is nothing to be done because these are just ammeters. The only thing we need to do is we need to check the direction. Now, as I've already said, that when we look at the forward converter, this is different in dot polarity from the flyback converter. In the flyback converter, if the dot on the primary winding is in the upper terminal, the dot on the secondary winding is in the lower terminal, because that is a flyback converter concept. In the forward converter, this dot polarity comes back to the upper terminal, which means all these components will reverse in direction. So we will have to make that change. So winding 1 stays as it is, that is current flowing downwards. Winding 2 will change. The current will go back downwards. So we will make this 4i. And the same here as well. Winding 3. Now winding 3, however, actually let's cancel winding 3. I will do it later. So let me look at winding 3 at a later stage. So instead, let's jump to voltages. So now if you look at the voltages, so let's say for example, we have the ammeter, we have the control voltage source, and we have the variable resistor, right? So let me just save this. It doesn't matter. We're not making a change. Let's get back the usual form. So now we come back to the control voltage source. Now as you can see, the control voltage source on the secondary had been reversed, right? If you look at these two, in the case of the primary, it is 5G, that is the positive polarity is upwards compared to the component. Here it is downwards. So we need to make this reversal. It'll be 5i. And if we keep going, there is the variable resistor does not have a polarity, so we don't have to worry. The voltmeter does, right? So in the case of the voltmeter, again, we had made a change. For example, in the case of voltmeter 1, the positive polarity is upwards, whereas in the case of voltmeter 2, the positive polarity is moved downwards. This needs to be reversed. So let's make this 7K as well. Oh, actually that's a mistake. You can't make this 7K. It has to be 6K because, yeah. So you see, if you make a mistake, that is if you put the polarity to be the same as the component position, it won't save it. So it has to be 6K. And if we keep going, and I think this way we have now come back to the normal transformer ratio of a forward converter, alright, or the dot polarity. So we now have the dot polarity at the upper terminal for both the primary and the secondary. So now coming to the tertiary. What do we do with the tertiary? Now, as I said, the purpose of this tertiary is when the switch is turned off, this tertiary has to be able to freewheel the energy stored in this magnetic field of the transformer back to the DC supply. Alright, so when the switch is turned off, current has to flow in the upward direction, right, back to the source. So therefore, what do we do with the dot polarity? If the dot polarity is on the upper terminal, when the switch is turned on, the current will increase. The EMF will be such so as to oppose the cause which produces it. which means the induced EMF will have a positive polarity in the upper terminal, right, at the dot. Now, what should happen at this terminal? At this terminal, when the induced EMF has a positive terminal, this should not conduct, right? There should be no conduction, which means that here you want the induced EMF to be the induced EMF should have a negative polarity at the upper terminal, right? So therefore, the dot polarity has to be the downward terminal. Now, when the switch is turned off, the current will try to stop flowing, which means the induced EMF will oppose the cause which produces, and that is the decreasing current, which means the induced EMF will have a negative polarity at the upper terminal. And under those circumstances, the induced EMF and this winding will also have a negative polarity at the at the other dot polarity. When that means the positive polarity of the induced EMF is at the upper terminal. And if that is the case, this can now conduct current towards the DC supply, right? Because the induced EMF can now be reached such a magnitude that it will force a current back to the supply. As of course, we have to adjust the polarity of the diode. That will come next. So therefore, we need to adjust all these polarities to face downwards. So ammeter, of course, will be upwards, but all the other polarity will be downwards, because remember, whichever is the dot polarity, the current enters that polarity, right? And all the other voltages have a positive polarity towards the dot. So let's make that change. So winding, this will need to change. This can remain the same because it's upwards anyway, so this is fine, because this is winding 3, and this positive, the terminal of the polarity of the ammeter is towards the upward direction, which means it is into the dot, which is perfectly okay. Then comes the control voltage source. The control voltage source, however, has to be in the downward direction, right? So we have to change this. It is 26, and here let's put the tag as this winding 3 transformer 1. So it is a unique tag. The variable resistor, these are variable resistor for 1. This needs to be changed because I changed the and keep coming. These don't need to be changed. This needs to be changed. The only change is that we need to give it a tag. There is no polarity, so we don't have to worry about that. And the last is the voltmeter. The voltmeter will need to be reversed. So it is 26, it will become 28, and this will be 1000. And with this, I think we are done. Let's just scroll through. These are the 3 ammeters. For the winding 1 and winding 2, ammeter current directions are pointing downwards. That's perfectly okay. For winding 3, it is pointing upwards. Also okay. The control voltage sources for winding 2, for winding 1 and winding 2 are pointing upwards, which is okay. And the tags are okay. For winding 3, the polarity is pointing downwards, which is okay because the dot polarity is the lower terminal. For this is variable resistor of transformer 1 and transformer 2. There is no polarity. The tags have been adjusted. And these are the loss terminals. This is for winding 2 and the loss for winding 2. And this is, there is one thing which I missed. See, this is the variable resistance of winding 3 of transformer, and this is the loss factor. We have to adjust the loss factor. And this should do it. Yes, it is done. That is the loss factor. The voltmeter winding 1 and winding 2, polarity is towards the upper terminal, which is okay. For voltmeter for winding 3, polarity is the downward direction, which is also okay. So I think with this we are done. And finally we come to voltage source. Choose the file, voltage source params, and upload the file. So here everything should be the same except for this diode. The diode is what is new. Now let's go back and check what's happening with the diode. Now this diode is, the purpose of this diode is to prevent this winding 3, right, the third tertiary winding, from being energized under normal circumstances. This is only a freewheel winding. So which means this has to be adjusted, a polarity has to be adjusted in such a way that the current will flow towards the left, back towards the DC supply, right? So therefore the cathode has to move towards the left. So which means if the position is at 5G, it has to be 5F. Let's save it. And everything else is the same. The switch is the same. Let's look at the switch once, whether the position is okay. 1G, 1H, yes it is. No, it isn't. So it is, look, this needs to be changed. For example, the switch has to be in such a direction that the current will flow towards the right. Because when the switch is turned on, it energizes the primary winding. And if you see, the polarity is incorrect. It is 1F. It should be 1H instead, because we want to point it towards the right. And this is probably because we adjusted the polarity in this simulation with respect to the flyback converter, because we needed to add another branch. For these reasons, it's usually a good idea to scroll through your parameters once before you finalize them. Voltage source is okay, voltmeter is also okay. So I think with this we are done. Alright. So we have edited the parameters of our circuit. Right. The main changes have been with the transformer, where we reversed the dot polarity on the secondary winding, and we added the dot polarity in the tertiary winding. And finally, for the voltage source, we changed the polarity of the diode and updated the polarity of the switch. So these are the only changes which were necessary. So I will stop this lecture now, and in the next lecture we will continue with adding the control file. So as before, if you have any doubts, please do either comment or message me on social media or send me an email, whichever is your preference. Otherwise, I will see you next week, where we will continue with this converter. Thank you so much for watching, and see you soon. Goodbye for now.